In the year 1826, Sir Humphrey Davy, as President of the Royal Society, presented Mr. John Dalton with a Royal Medal for his development of the theory of definite proportions, usually called the atomic theory of chemistry. This presentation set an official seal upon the emergence as a scientific theory of an idea of matter which had existed for over 2,000 years as a belief, unsupported by experimental proof. In Dalton's time, chemistry was becoming an exact science, thanks to accurate methods of weighing and analysis introduced in the 18th century. Dalton was able to work out fairly accurately the relative combining weights of many elements. In his new system of chemical philosophy, published in 1808, Dalton pointed out that these combining weights, which are constant for each particular compound, must be related to the weights of the ultimate particles or atoms of the combining elements. Thus, the atomic theory was reborn. According to Dalton, firstly, matter is composed of small particles which cannot be split up any smaller. These particles he called atoms. Our diagrams illustrate his ideas, but not, of course, the real shapes of atoms. He believed, secondly, that all atoms of one element are exactly alike, and differ from the atoms of other elements, and have a characteristic relative weight. Thirdly, he believed that atoms are indestructible, and cannot be created. Fourthly, that chemical combination occurs between small whole numbers of atoms. Such combinations of atoms are now called molecules. In any given compound, all molecules are alike. Dalton invented a system of symbols to represent the atoms of the different elements. He used these to show how the atoms combined to form molecules. Though some of his conclusions proved wrong, atomic theory was the foundation upon which the chemistry of the 19th century was built. Painstaking chemical analysis based on Dalton's theory and research arising out of Avogadro's hypothesis concerning molecules and gases enabled accurate atomic weights to be assigned to the elements. A connection was sought between atomic weights and chemical properties, and in 1869 this was supplied by Mendeleev's periodic table, which arranged all the elements then known in families according to their atomic weights and properties. Thus, the column headed by carbon contains a group of elements with closely similar properties. The next column contains another group of similar elements, and so on. Now, from left to right, the elements are arranged in ascending order of atomic weight. The whole table fits together like a puzzle. The properties and place in the table of unknown elements were predicted, and the discoveries of later years proved the accuracy of these forecasts. The decomposition of solutions by an electric current was used as a means of chemical analysis in the early 19th century. By careful measurement, Michael Faraday was able to show that in such cases a definite quantity of electricity was associated with definite amounts of the elements produced at the electrodes, that is, with definite numbers of atoms. Hence, he suspected that electricity itself might be atomic by nature. It was established that there were two kinds of electricity. Unlike charges attracted each other. Like charges repelled each other. By convention, these two kinds of electric charge became known as positive and negative. In a solution like common salt in water, the sodium chloride exists as ions or charged atoms of sodium and chlorine. When the solution is electrolyzed, the positive sodium ions travel towards the cathode and the negative chlorine ions to the anode. The work of many scientists on liquids and gases led to the theory that in all matter, molecules are in a state of perpetual motion. The botanist Robert Brown was the first to see in his microscope what is now called Brownian motion. This is the intricate motion imparted to fine particles in suspension in a liquid by the impact of molecules. One can imagine the tiny particles being pushed about by these ceaselessly active molecules. Each molecule is so small that 27 million are contained in 1 cc of gas at 0 degrees centigrade and normal pressure. The thinnest soap bubble that can be made by ordinary means is about 1/100,000th of a centimeter thick. In this space, about 1,000 molecules could lie side by side. Each of these molecules would be 3 or 4 times the size of a small atom. This much was known at the close of the 19th century, which Lord Rutherford sums up in these words.
At the close of the 19th century, the labours of the chemist had resolved the matter of our material world into 80 or more distinct elements, and the atoms of these elements appeared to be permanent and indestructible by the forces then at our command.